So this time we're taking a look at section 12.2, which deals with vectors. So the term vector indicates a quantity that has both a magnitude and a direction. And typically we're going to use an arrow or a directed line segment to represent a vector. So for example, you might have a vector like so. We have a point A here and a point B there, and it looks like this directed line segment is going from A to B. Now, we could refer to this as the vector AB, or we could refer to it as the vector B, and we'll put an arrow above the V to indicate that yes, this is a vector. Now in the book you'll see this written as a bold V instead of a V with an arrow over it. But this vector, you say V equals AB, has an initial point A, and a terminal point B. Now, if I were to take this vector and move it anywhere along the board, while maintaining the same direction and the same magnitude, I would say that I'm really dealing with the same vector or equivalent vector. So if I were to take a look at a vector like this, let's try to draw it so that that's pretty good comparison to the AB vector here. Yeah, pretty close. So let's pretend that this is going in exactly the same direction that the vector AB is. So if we were to say that this is a vector U, so U would equal a vector CD. Now, if this vector U has exactly the same magnitude and direction as V, then we would say that U and V are equivalent or equal vectors. So once again, if U has the same magnitude and direction as V, then U and V are equivalent or equal. And we would say that U equals V. Alright, so in this section we're really looking at an introduction to vectors. There's going to be a lot of terminology and therefore lots of definitions. So let's take a look at the following. This is the definition of the zero vector. So the zero vector, which is denoted by either a bold 0 or 0 with an arrow above it, has 0 length, and no specific direction. All right. Now, next definition. Let's suppose we have u and v are vectors. So once again, u and v are vectors. And these are going to be positioned so that the initial point of v is at the terminal point of u. So once again, if u and v are vectors, so that the initial point of v is at the terminal point of u, then we can take a look at the sum of u and v of these two vectors. And this sum is going to be a vector itself. This is going to be from the initial point of u to the terminal point of v. Now, this is a very wordy definition, and it's probably a heck of a lot nicer just to see a picture of what's going on. So let's go through the definition. Let's form our picture from that. All right, so we have u and v are vectors, and they are positioned such that the initial point of v is at the terminal point of u. So you might have your vector u that looks something like this. So here's the initial point of u, and there's the terminal point of u. Now what we're saying is that the initial point of v is at the terminal point of u. Okay, the initial point of v is going to be at this point, then, the terminal point of u, and maybe v looks something like this. So maybe that's your vector v. Initial point of v is going to be at the terminal point of u. Then the sum of u and v is going to be the vector that goes from the initial point of u, which is right here, to the terminal point of v, which is right there. So your sum of u and v will be defined that way. All right. Now, for our next definition, we've got a note that says that we may multiply a vector by a real number c. That real number is called a scalar. And so with this note, we can start thinking about what's referred to as scalar multiplication. And that leads us to our next definition. So if v is a vector, and if c is a scalar, then the scalar multiple which we're going to call c times v is the vector whose length is the absolute value of c times the magnitude of v. So if you have a vector v and let's say c is 2, then 2 times v is going to be twice the magnitude of v. But at the same time, if c is negative 3, we're not going to say the magnitude is negative 3 times magnitude of v. No. If we have negative 3 of v as a scalar multiple, then the length of that scalar multiple is going to be actually 3 times the magnitude of v. But what we have to keep in mind is that the direction is going to be the same as the direction of v if the scalar is positive and the direction of CV is opposite the direction of A. If C is negative. Alright, so once again, the length of CV is going to be absolute value of C times magnitude of A. And CV and V will have the same direction if C is positive, and opposite directions if C is negative. Now, if your scalar is 0 or your vector is the 0 vector, then CV will be the 0 vector. Now, one thing to keep in mind is that if we had a vector V that looks like this, for example, then 2 times V you'd have the same direction, but this vector would be twice the length of the original. And then let's say you want a negative V. Or negative 1 times V. Well, you'd have the same magnitude as V, but opposite direction. So in this case, C would be negative 1. In this case, C is positive 2. But notice that when C is positive, the scalar multiple has the same direction as V, and when C is negative, the scalar multiple has opposite direction as V. All right, so we have a few more definitions. So in this definition, we have 2 non-zero vectors. We say that these are parallel if they are scalar multiples of each other. Now, if the vectors are both non-zero and they're scalar multiples of each other, then that means that they either point in the same direction or they point in opposite directions. And yet another definition. So with this one, we take a look at the difference U minus V of 2 vectors U and V. Is defined as follows. U minus V is equal to U plus a negative V. So U plus a negative V. Well, if you think about U plus a negative V, let's say that we have a similar situation as before. We've got vector u. It looks like this. We've got a vector v that, let's say we put both terminal points at the same spot. Or sorry, both initial points. Both initial points at the same spot. And then your picture would look like this. Now, negative v would have the same magnitude as v, but it would just point in the opposite direction. So if I were to take this vector and make sure that I put this point here, but pointing in the opposite direction, then this would be negative v. And our vector u minus v would look something like this. Now, I will say that that's not necessarily exactly how I always like to think about it. So let me show you a perhaps different approach. In fact, we can go back to this particular figure. We already know that this vector is the same thing as u plus v. But imagine forming a parallelogram. And this parallelogram is going to be formed in such a way that we shift this v over here so that the initial point of v and the initial point of u are the same. So we would have our vector v like this. And then our vector u would look like this. So we've got this nice parallelogram formed. And one thing to keep in mind too is that if you go back to the way that the sum of two vectors is defined, if we think about putting the initial point of v at the terminal point of u, then this vector here is u plus v, of course. But here we've put the initial point of u at the terminal point of v. So v plus u would be this blue vector as well. And so that would seem to indicate that we have sort of a commutative property for adding these vectors together. Now, if I were to erase this vector, and let's say that I draw a vector that goes across the other diagonal, notice this blue vector has this initial point at the terminal point of v. That means that v plus this vector is equal to u. Now how can we pull that off? Well, this vector would then be u minus v, because v plus u minus v, oh, check it out. The v and the negative v cancel out. You're left with u. And so this is another way that you could think about the u minus v. Also, another way to consider it is if I were to take the vector v, switch the direction, keep the initial point here, terminal point is going to be here, I'm going to have a vector that goes across, which is going to be pointing in exactly the same direction as u minus v anyway. So, just different ways to think about what's going on with the difference. All right. So let's take a look at an example. So I'm going to draw two vectors, a and b, and we're going to draw a minus 2b based on them. And so our vector a, we're going to draw like this, and our vector b is going to look like this. So if we think about a minus 2b, well, a is going to be like so. So we'll take a look at it. It looks like it has about the same magnitude. B would be pointing in this direction, so negative 2b would be pointing in the opposite direction. And so if we were to take a look at putting negative 2b, the initial point of negative 2b, at the terminal point of A, then basically what we would have is a picture that looks something like this. So let's go for, looks like that's about negative 2b here. So I've got the initial point of negative 2b at the terminal point of A. So if I take A plus a negative 2b, same thing as A minus 2b. And then I'm going to draw this vector from the initial point of A to the terminal point of negative 2b. And so that'll be our A minus 2b right there. Okay. So once again, there are lots of definitions, there's lots of terminology in this section that we're going to be using over and over as time goes by. The next part to this section, however, deals with what are called components. Alright, so here we suppose that the initial point of a vector A is at the origin. And let's say that the terminal point has coordinates A1, A2. Or maybe we're in three-dimensional space, in which case the coordinates of the terminal point might be A1, A2, A3. Now these coordinates are called the components of A. And in the first case, we would write A with this sort of notation. We'll have the A1 and the A2. Or in the second case, we'll have three components. So this would be our component form for the vector A in two-dimensional space, and this would be the component form for the vector A in three-dimensional space. But notice that this is based upon the positioning of the vector so that the initial point is at the origin. And so the components, or sorry, the coordinates of the terminal point are going to just be the components of the vector A. Now, one thing to make note of is given the points A with coordinates x1, y1, and z1, and B with coordinates x2, y2, and z2. And the vector A with representation like so. It's going to be as follows. We'll have A. First component will be x2 minus x1. Second component, y2 minus y1. Third component, z2 minus z1. Now, if you think about why that is the case, notice that the way this is written out, the initial point is capital A, terminal point is capital B. And so if you go back to the previous section video, when we were taking a look at the distance between 2 points, remember when we were verifying why the distance formula was what it was, there was this idea of shifting points. And that idea is really central to what's going on here. So if you were to take a look at a situation like the following, where you have a vector where here is your point A and here's your point B, maybe the image of the point A in the xy plane looks something like this. And maybe the image of the point B in the xy plane, maybe it looks something like this. Who knows? But one thing that we do know is that if we're looking for the component form for this vector A, then we better have the initial point at the origin. Now, if this point A has x1, y1, and z1 as coordinates, and the point B has x2, y2, and z2 as coordinates, then shifting A to the origin means subtracting x1 from the first coordinate of A, subtracting y1 from the second coordinate of A, and subtracting z1 from the third coordinate of A. Doing that will shift this point to the origin. So now your initial point will be located at the origin. However, if you're wanting to maintain the magnitude and the direction of this vector A, then the point B has to be shifted exactly the same way. And so if we subtracted x1 from the first coordinate of A, we're going to have to subtract x1 from the first coordinate of B. If we subtracted y1 from the second coordinate of A, we got to subtract y1 from the second coordinate of B. And finally, if we subtracted z1 from the third coordinate of A, we've got to subtract z1 from the third coordinate of B. And so what happens is when we take a look at the new location of the terminal point, it's going to be at x2 minus x1, comma y2 minus y1, comma z2 minus z1. So those will be the coordinates of the terminal point if the initial point of the vector is at the origin. And how do you get the component form of your vector? Well, initial point needs to be at the origin, and these end up being the coordinates of the terminal point. What it means is that if we're given a vector from A to B, then we can get the component form of that vector by taking terminal point coordinates minus initial point coordinates. And this next example will illustrate just that. All right, so for this example, we'll find the vector represented by the directed line segment with initial point A, which has coordinates 2, negative 3, and 4. And terminal point B and B is going to have coordinates negative 2, 1, and 1. All right. So once again, we're going to find basically the component form of this vector. And in order to do this, the initial point will have x1, y1, and z1 as its coordinates. Terminal point will have x2, y2, and z2 as its coordinates. And so we got to figure out our solution here. We'll have, once again, x2 minus x1 is the first component, y2 minus y1 is the second component, and z2 minus z1 is the third component. We already have the labels here, and so we'll just plug in the appropriate numbers where they're supposed to show up. And so with our vector A, x2 is negative 2. Subtracting x1, so we're subtracting 2. y2 is 1. We're subtracting y1, which is negative 3. And then z2 is 1. Subtracting z1, subtracting 4. And so when you work this out, negative 2 minus 2 gives you negative 4. 1 minus negative 3 is 1 plus 3, which is 4. And then 1 minus 4 is negative 3. So there's your component form for that vector A. Now keep in mind that basically what's going on here is that if we were to shift the vector so that the initial point is located at the origin, and the terminal point would be at the location negative 4, 4, negative 3. All right. Now this next definition is of the magnitude. Now I've already used that word in this video, but magnitude of a vector is just the length of the vector. So the magnitude or length of vector B is the length of any of its representations. And just denoted by, you'll see vector v with what looks like absolute value sign, or sometimes you'll see sort of a doubling up. So either one of these represents the magnitude of v. And if we have a vector A whose component form is what we're seeing here with components A1 and A2, and then the magnitude of A square root of A1 squared plus A2 squared and if we're looking at a vector in 3 space, then the magnitude of A is going to be the square root of A1 squared plus A2 squared plus A3 squared. Now, this is a direct consequence of the distance formula. So if you were to take a look at the distance, let's say in this case, the distance between the point 0, 0, 0 and the point A1, A2, A3, that distance will be given to you by this formula here. This is once again direct application of the distance formula. And we already saw how that distance formula works back in the video for the last section. All right. So let's take a look at another note here. So let's say we have A as a vector with components A1 and A2, and B is a vector with components B1 and B2. have this rule that A plus B is going to look like this. Now, one way to visualize what's going on here is if you have, let's say, two vectors in two-dimensional space. Suppose we have the vector A looks something like this. The vector B that looks something like this. Well, the terminal point of the vector A has coordinates A1 and A2. So you'll have A1 there, and then you'll have A2 there. The terminal point of B will be located at B1, B2. So this terminal point will have, you'll have B1 there, and then you'll have B2 there. So in other words, to get from the initial point of B to the terminal point of B, you would have to move to the right B1 units and move up B2 units. Now think about how you add A and B together. We take the initial point of B, put it at the terminal point of A. So you're going to have a picture that looks something like this. Now this point right here is already A1, A2. So I've already mentioned that in order to get from the initial point of B to the terminal point of B, you have to move to the right B1 units. You have to move up B2 units. That means you have to add B1 to A1 to have moved far enough horizontally. And then you would have to move up B2 units to have moved up far enough vertically. So if your starting point is at A1, A2, and I have to move to the right B1 units, then x-wise I'm now at A1 plus B1. And if I have to move up B2 units, then y-wise I'm now at A2 plus B2. And so that's where the terminal point of this repositioned vector B is located. But remember, A plus B, you go from the initial point of A to the terminal point of B with those vectors positioned the way they are here. So we take a look at A plus B, and now A plus B has initial point at the origin, has terminal point here, so those become the components of A plus B, which is exactly what we see here. Now, in a similar fashion, A minus B we'll get by having first component A1 minus B1, second component A2 minus B2. And if we take, let's say, a scalar multiple of A, take C times A, CA1 will be our first component, and then CA2 will be our second component. Now, we can do the same sort of thing for vectors in three-dimensional space. So if we have A with components A1, A2, and A3, and B has components B1, B2, and B3. Then again, we can take a look at A plus B, A minus B, C times A, and we'll find very similar results here. So A plus B will have components A1 plus B1, A2 plus B2, A3 plus B3. So exactly the same kind of thing you're seeing here, just with a third component of A3 plus B3 kind of added on to the end. Second part of this, you take A minus B. That'll give us A1 minus B1, A2 minus B2, A3 minus B3. And then finally, if we take C times A, then the components will be CA1, CA2, and CA3. All right, so let's take a look at an example where we use some of these ideas. And let's say that we have a vector A whose components are 4, 0, and 3. And a vector B with components negative 2, 1, and 5. Then we're going to find the magnitude of A. We'll also find the vectors A plus B, A minus B, (3b), and finally 2a plus 5b. All right, so let's start with magnitude of A. Now, one way that I like to describe the magnitude of a vector A is as the square root of the sum of the squares of the components of A. So once again, the magnitude of a vector is the square root of the sum of the squares of the components. Now, one reason I like that description is both this equation and this equation fit that description, square root of the sum of the squares of the components. So if I'm going to figure out the magnitude of A here, I need to take the square root of, once again, the sum of the squares of the components. The components are 4, 0, and 3. I have to square each one of these. Add those together, and then take the square root. So magnitude of A is the square root of 4 squared plus 0 squared plus 3 squared. And that means the magnitude of A is the square root of 16 plus 0 plus 9. 16 plus 0 plus 9 gives you 25. And so as a result, we have magnitude of A is 5. All right, so that's the first part, but we also have the vectors A plus B, A minus B, 3b, and 2a plus 5b to figure out. So let's take a look at A plus B. And so here I've written out the A plus B in the component form. And really it's just a matter of adding corresponding components together to get your final answer. So the first component of A plus B is 4 plus negative 2. That gives you 2. Second component of A plus B is 0 plus 1. That gives you 1. And the third component of A plus B is 3 plus 5, and that's 8. And that's not too bad. So next on the list is A minus B. And just like before, I'll go ahead and write this out in component form. It's just this time we're subtracting B from A. But really this is about the same level of difficulty because the first component of A minus B is obtained by taking 4 minus a negative 2. Well, is 4 plus 2, gives you 6. Second component of a minus b is 0 minus 1, that's a negative 1. And the third component of a minus b is 3 minus 5, and that is negative 2. Next on the list is 3b. So we're going to take 3 times the vector with components negative 2, 1, and 5. And this is also really nice because all we have to do is multiply each of the components of b by 3. And so the first component of 3b is 3 times negative 2, or negative 6. Second component of 3b is 3 times 1, which is 3. And the third component of 3b is 3 times 5, which is 15. And then last on the list is 2a plus 5b. So we'll have 2 times the vector with components 4, 0, and 3, plus 5 times vector with components negative 2, 1, and 5. Alright, so if we take 2 times this vector a, 2 times 4 gives us 8, 2 times 0 gives us 0, 2 times 3 gives us 6. When we add, then we'll have 5 times negative 2 is negative 10, 5 times 1 gives us 5, 5 times 5 gives us 25. At this point we have a sum of 2 vectors, and this goes back to the kind of thing we saw in this part. Just add the corresponding components together. You'll have 8 plus a negative 10 gives you negative 2. We'll have 0 plus 5 gives us 5. And then finally 6 plus 25 gives us 31. So negative 2, 5, and 31 are the components of that last vector that we were asked to come up with. All right. So I've got another note that I would like to put up here. And so in this note, we're saying that we're going to denote by V2 the set of all two-dimensional vectors and by V sub 3 set of all three-dimensional vectors Well, if that's the case, then we have capital V sub n is the set of all n-dimensional vectors. Now, an n-dimensional vector is an ordered n-tuple and we can write this as a vector A with components a1, a2, all the way through a sub n. And then a1 through a sub n are real numbers. And these are the components of A. All right, so let's let's take a look at some properties of vectors. All right, so the properties of vectors. Let's dive into that. Now, if you've taken, let's say, a standalone course in linear algebra, these properties are probably going to look very familiar. You might remember them as the vector space axioms. I'm not going to get into all the gory details of that here, but I will list out the properties. So let's say that A, B, and C let's say A, B, and C are vectors in V sub n, and we'll let C and D be scalars. Now, if you're worried about reusing C here, we're not really reusing it from the standpoint of, notice that this C has an arrow above it, which indicates it's the vector C, where this C does not have an arrow over it, which means it represents the scalar C. So just be mindful of the difference in notation, the vector versus the scalar. Now, first property that we have is A plus B is equal to B plus A. That is the commutative property holds here. Now we also have the associative property in number 2. So if we have the vectors A, B, and C added together, let's say somebody wants to add B and C first and then add A to that result. Somebody else wants to add A and B first and add C to that result. Well, if they do it right, they're going to get the same thing. Property 3, A plus the 0 vector is equal to A. Which means we have basically 0 as our additive identity for this vector space. We have A plus negative A, it's the 0 vector, so that accounts for additive inverses. And then the next 3 or so, then we start taking a look at these scalars. So for number 5, we have the scalar C times the sum A plus B. And that's the same thing as C times A plus C times B. So this means that scalar multiplication is distributive over vector addition. Number 6 has us taking a look at C plus D times A. And that's going to give us CA plus DA. Number 7 has us taking a look at C times D times A. Once again, scalar C here. And essentially what this is telling us is that if we have 2 scalars, C and D, that we could multiply the scalars together first, and then multiply that result by A. Or we could multiply A by one of the scalars first, and then multiply that result by the other scalar. And then the last one is if you take 1 times A, that's just going to give you A. Now, I don't think that any of these properties are especially just surprising, but they're valid, so it's good to know about them. But as I said before, if you have taken a standalone linear algebra class, or if you do at some point in the future, then you'll be getting pretty familiar with those. All right. Now going back to the definition, we have the vectors I. Now this vector I in 3 space is going to have components 1, 0, and 0. Vector J has components 0, 1, and 0. And the vector K has components 0, 0, and 1. Now these are called the standard basis vectors. Now, once again, if you take a course in linear algebra, you'll certainly see the term basis come up over and over again. But once again, I'm not planning on getting into a lot of gory details with regard to linear algebra. Now, once again, I, J, and K are what we refer to as the standard basis vectors. Now, some of you may be familiar with notation where you have I, J, and K with hats over them. And if that's how you want to write them, go for it. It's not a big deal. I'm going to keep the arrow notation, but if we're in 2 dimensions, we don't have our K vector. We do have I and J. And vector I will have components 1 and 0. And vector J will have components 0 and 1. Now, if you think about what this looks like geometrically in 2 dimensions, your vector I, once again, if the components are 1 and 0, that means when the initial point is at the origin, the terminal point will be at 1, 0. So your vector I will be along there, and then your vector J, in a similar fashion, will be this vector along here. And so it turns out that every vector in 2-dimensional space can be written as something times I plus something times J, because the I vector, essentially when you multiply by a scalar, is going to handle the horizontal movement, and the J vector, when you multiply by a scalar, is going to handle the vertical movement. So no matter where your terminal point is for the vector that you're wanting, you're going to move a certain distance horizontally, a certain distance vertically, and so something times I plus something times J will be a valid representation no matter what vector it is that you're considering in 2-dimensional space. Similar fashion, 3 dimensions. So you have 1 here, 1 here, 1 there, X, Y, and Z axes. And if you take a look at the vector I, that'll be this vector here. Right, so there's I. Vector J will be along there. And the vector K will be along there. And so once again, if we have any vector in 3-dimensional space, we'll be able to write it as something times I plus something times J plus something times K. And in fact, if we go back to our component form, if we have A with components A1, A2, and A3, then that means that A is the same thing as A1I plus A2J plus A3K. Now, with that in mind, let's take a look at the following example. So let's suppose we have a vector A. And maybe A is represented as I plus 2j minus 3k. And let's say we have the vector B that's equal to, let's say, 4i plus 7k. And what we're going to do is we're going to represent 2a plus 3b in terms of I, j, and k. All right, so the way this goes is that if we take 2a plus 3b, that's going to be the same thing as 2 times the vector I plus 2j minus 3k plus 3 times the vector 4i plus 7k. Now, if we take 2 times I plus 2j minus 3k, that's the same thing as 2 times I plus 4 times j minus 6 times k. And then we're adding 3 times 4i plus 7k, which means we're adding 12i plus 21k. Now, if you take a look, you've got a 2i plus 12i gives you a 14i. You have a 4j, but no other j vectors, so the plus 4j. And then finally, we have a negative 6k and a 21k, and that gives us a 15k. Now, in terms of component form, yeah, we would have 14, a 4, and a 15. So that would be our 2a plus 3b. But written this way, we say that 2a plus 3b is written as a linear combination of I, J, and k. All right. There is one last part to this section. We have one more definition and one more example. And this definition is that of a unit vector. Unit vector is a vector with magnitude 1. And in general, if A is not the zero vector, then the unit vector has the same direction as A. and is defined as U equals 1 over the magnitude of A times A. Now, the magnitude of A is going to be positive if the vector A is not the zero vector. So U is a positive scalar times A, which means that U and A are pointing in the same direction. The real trick is, well, do we really have magnitude 1 here? So think about what would happen if A has components A1, A2, and A3. Well, we're going to know the magnitude of A is the same thing as the square root A1 squared plus A2 squared plus A3 squared. So if we take a look at the magnitude of U, well, first off, U is going to be 1 over magnitude of A times A. Which can be written as 1 over square root of A1 squared plus A2 squared plus A3 squared times the vector with components A1, A2, and A3. Now, that means that U can be written as the following. Okay, so once again, this is what our vector U looks like. So if we take the magnitude of U, square root of the sum of the squares of the components, and this is going to look really horrible at first. But one thing that's nice is that for each of these fractions, we just put the square of the top over the square of the bottom. And so for this first part, we'll have an A1 squared over, then we take the square root of A1 squared plus A2 squared plus A3 squared, raised to the second power, and that's just going to give us A1 squared plus A2 squared plus A3 squared. Similar fashion, we'll have an A2 squared over A1 squared plus A2 squared plus A3 squared. And we'll also have an A3 squared over A1 squared plus A2 squared plus A3 squared. Now, one thing that's really nice about this is we have exactly the same denominator for each of these three fractions. So this turns into the square root of A1 squared plus A2 squared plus A3 squared when we add along the top over A1 squared plus A2 squared plus A3 squared, which is our common denominator. And of course, you take a look at this and you notice exactly same numerator as denominator. This is 1. Square root of 1 is equal to 1, so we definitely do have a unit vector. So for our last example, let's take a look at finding the unit vector in the direction of the vector. We'll have A equals 2I minus j minus 2k. All right. So another way that we could write this is we could say, let's put this in component form. And the components of A are 2, -1, and -2. And what we're interested in is figuring out what the magnitude of A is. Because after all, if our goal is to find the unit vector, that's defined as 1 over magnitude of A times A. And so we'll have the square root of the sum of the squares of the components. So the square root of 2 squared plus the square of -1 plus the square of -2. Now, 2 squared gives us 4. Square -1, you get 1. Square -2, you get 4. And then 4 plus 1, 5 plus 4 gives you 9. Square root of 9 is 3. So if you have the magnitude of A, it's a heck of a lot easier to figure out what the unit vector is in the direction of A. And so in this case, we'll have U, 1 over magnitude of A times A. And magnitude of A is 3, so we'll have 1/3 times the vector A, which has components 2, -1, and -2. And so if you work this out, we have a scalar multiple, right? 1/3 times this vector A. So you can multiply each component here by the 1/3. And that'll give you U, the vector of components. So 1/3 times 2 gives you 2/3. 1/3 times -1 gives you a -1/3. And 1/3 times -2 gives you a -2/3. And if you decide to write this in terms of a linear combination of I, j, and k, that will be the same thing as 2/3 I minus 1/3 j minus 2/3 k. And with that, section 12.2 is finished. So our recommended exercises: 9, 13, 15, 17, 19, 21, 23, and 25.